Today we are going to start Chapter 10. In Chapter 9, we looked at hypothesis tests where we are comparing one proportion or one mean against a number. In Chapter 10, we are going to compare two different populations. We'll look at proportions in this video, and we'll look at means in the next video. So, let's take a look at this example. In one school, 70% of students did their homework last night. So P1 is 0.7. At school 2, 50% of their students did homework last night. So P2 is 0.5. Now, a counselor at school 1 selects a simple random sample of 100 students and records the proportion that did their homework. We will represent this as P hat 1. Remember that P is the population proportion, P hat is the sample proportion. School 2's counselor selects a simple random sample of 200 students and records the proportion P hat 2 that did their homework. So, we have a little chart here. We have two different populations. The parameter is P, the statistic is P hat, and the sample size is N. Subscript of 1 is everything referring to the first population. Subscript of 2 is everything referring to the second population. Now, we can look at the sampling distributions for both P hat 1 and P hat 2. Both are approximately normal. If you check the large counts condition, which is n times p and n times 1 minus p, they all give you numbers that are greater than 10. The center is just going to be the population proportion, which is 0.7 for the first sample, or for the first population, 0.5 for the second. And we can calculate the variability using a formula on our formula sheet. Remember, when we're checking conditions, we have to check that n is less than 10% of the total number of students at the school. But what we're really interested in here is the difference in the sample proportions. You can do either P hat 1 minus P hat 2 or P hat 2 minus P hat 1. It doesn't really matter as long as you're consistent. Here we're looking at P hat 1 minus P hat 2. So, one set of samples gave us P hat 1 of 0.72, P hat 2 of 0.47. So the difference is 0.25, represented by that dot on the dot plot there. Now, the mean of this sampling distribution is just going to be the difference of the means of the original sampling distributions, so 0.2. And you can calculate the standard deviation using a somewhat complicated formula, but it is on your formula sheet. If I look at my formula sheet, look at the second page. If you look at sampling distributions for proportions and look at two populations, right here it gives you all of this information. We can find both the mean and the standard deviation of that sampling distribution. Now, let's continue. If we have a simple random sample of size n1 from population 1 with proportion of successes p1, and an independent simple random sample of size n2 from population 2 with a proportion of successes p2, then we know that the sampling distribution of p hat 1 minus p hat 2 is approximately normal if the large counts condition is met for both samples. We can find the mean of the sampling distribution very easily, and we can use a formula to calculate the standard deviation as long as the 10% condition is met for both samples. So, we take a look at this first question. Your teacher brings 2 bags of colored Goldfish crackers to class. Bag 1 has 25% red crackers, bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1 and a separate simple random sample of 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportions of red crackers. What is the shape of the sampling distribution of p hat 1 minus p hat 2? If you look at the first condition on the previous slide, you know that the sampling distribution is approximately normal if the large counts condition is met for both samples. Meaning that you have more than 10 red and 10 non-red goldfish in each sample. Which, if you do the math, we do. To find the mean of the sampling distribution, all we do is subtract the proportions that were given for each bag. 25% minus 35% is negative 10%. Then, to calculate and interpret the standard deviation, you use the formula to calculate it, and because the 10% condition is met, we can use the formula. We know that 50 is less than 10% of all crackers in bag 1, 40 is less than 10% of all crackers in bag 2, because we're told that both bags have more than 1,000 crackers. So we can use this formula and get our standard deviation. Then we need to interpret the standard deviation, which is going to be the same as it has been all year. The difference, and typically you specify which difference. You're doing bag 1 minus bag 2. In the sample proportion of red goldfish crackers typically varies by about 0.097 from the true difference in proportions of negative 0.1. Remember, when you're interpreting the standard deviation, you need to say the thing that we're looking at typically varies by whatever the standard deviation is from the true, whatever the mean is. So, first we're going to look at confidence intervals. There are 3 conditions, and they're the same 3 conditions as we had in the previous chapter when we were only looking at one proportion. First, you need a random sample. The data comes from 2 independent random samples or from 2 groups in a randomized experiment. We have the 10% condition, that the sample size needs to be less than 10% of the population in both cases. And then the large counts condition. The number of successes and failures in each sample or group needs to be at least 10. Next situation. A Harris Interactive survey asked independent random samples of adults from the United States and Germany about the importance of brand names when buying clothes. Of the 2,309 U.S. adults surveyed, 26% said brand names were important, compared to the 22% of the 1,058 German adults surveyed. Let P sub U be the true proportion of all U.S. adults who think brand names are important when buying clothes, and P sub G be the true proportion of all German adults who think brand names are important when buying clothes. Check if the conditions for calculating a confidence interval for PU equals PG are met. So, our first condition, do we have random samples? Yes, it specifically says that we have independent random samples of adults from the US and Germany. Next, we have the 10% condition. It's pretty safe to say that 2,309 is less than 10% of all US adults, and 1,058 is less than 10% of all German adults. The last condition is the large counts. So you do n times p, n times 1 minus p for both samples. And as long as all of those numbers are greater than or equal to 10, which they are, we're good. So all of our conditions are met. So when we are doing confidence intervals, we're using the same basic format as we did in previous units. We have the statistic plus or minus the critical value times the standard deviation of the statistic. In this case, that is p hat 1 minus p hat 2 plus or minus z star times the standard deviation of the statistic. Now, if you look at your formula sheet, this is the formula that we use for standard deviation. This uses P1 and P2, which are the population proportions, which we don't know. The standard error formula uses P hat 1 and P hat 2 to estimate the standard deviation. So this is what you want to use. And this is again on your formula sheet. The third column is standard error of the statistic. We have two formulas here, which we'll talk about the difference between those in a minute. So, for a two-sample Z interval for difference between two proportions, if your conditions are met, a C% confidence interval for P1 minus P2 is given by this formula here. Z star is the critical value for the standard normal curve with C% of the area between negative Z star and positive Z star. Same setup as we used in the past. So far we've focused on doing inference using data that were produced by random sampling. The following example shows how to construct and interpret a confidence interval for a difference in proportions from a randomized comparative experiment. So, here's the situation. Patients with lower back pain are often given non-steroidal anti-inflammatory drugs, or NSAIDs, like naproxen, to ease their pain. Researchers wonder if taking Valium along with a naproxen would affect pain relief. To find out, they recruit 112 patients with severe lower back pain and randomly assign them to one of two treatments, naproxen and Valium, or naproxen and placebo. After 1 week, 39 of the 57 subjects who took naproxen and Valium reported reduced lower back pain compared to 43 of the 55 subjects in the naproxen and placebo group. So, clearly we have an experiment. We are taking two treatments and applying them to two different groups. We want to construct and interpret a 99% confidence interval for the difference in the proportion of patients like these who would report reduced lower back pain after taking naproxen and Valium versus after taking naproxen and the placebo. So, we are going to use state, plan, do, conclude format. we are looking at a 99% confidence interval for P1 minus P2, where P1 is the true proportion of patients like these who would report reduced lower back pain after taking naproxen and Valium for a week, and P2 is the true proportion of patients like these who would report reduced lower back pain after taking naproxen and a placebo for a week. So we state what we're doing and define our parameters. Plan, we need to check our conditions. We're looking at a 2-sample Z interval for P1 minus P2. The patients are randomly assigned to the treatment groups, and the large counts condition is met. Because there are more than 10 people who reported reduced lower back pain and did not report reduced lower back pain in both treatment groups. In an experiment, you do not need to worry about the 10% condition. Then, on to the do step. We can figure out what p hat 1 and p hat 2 are by just dividing the numbers given in the problem. Once you have that, all you need is p hat 1, n1, p hat 2, and n2 to figure out your confidence interval. So you plug everything into the formula and do the math. Then, for conclude, we need to interpret this. We are 99% confident that the interval from negative 0.312 to 0.116 captures P1 minus P2, which is the difference in the true proportions of patients like these who would report reduced pain after taking naproxen and Valium versus after taking naproxen and the placebo for a week. Part B. Based on the confidence interval in Part A, what conclusion would you make about whether taking Valium along with naproxen affects pain relief? Well, because the interval includes 0 as a plausible value for a P1 minus P2, we do not have convincing evidence that taking Valium along with naproxen affects pain relief for patients like these. If 0 was not in the interval, so if the entire interval was positive, then there would be evidence to suggest that taking Valium along with naproxen reduces pain or increases pain relief. But be careful. Never say that you believe that the difference between the two proportions is 0 just because 0 is in the interval. We are merely saying that because 0 is a plausible value, we cannot conclude that Valium along with a naproxen affects pain relief. Now, you can do this on your calculator. If you have a TI calculator, you're going to follow these steps exactly. If not, use one of the TI emulators that I suggested. The interface is almost identical to what's presented here. Ultimately, you are looking for the 2-prop Z int. If you go to Stat, Tests, 2-prop Z, not a Z test, Z interval, 2-prop Z int, which on my calculator is B. You input X1, which is the number of successes, so the number of people who had reduced pain, N1, which is the total number in the first group, X2, which is the total number who had reduced pain in the second group, and N2. Then put your confidence level and hit calculate. it will spit out your interval along with the proportions. And that's your interval. Now, let's go ahead and take a look at significance tests. So, for a significance test, our null hypothesis is going to be P1 minus P2 equals a number. The most common situation is we are looking to see if the difference is 0. So this null hypothesis is equivalent to saying P1 equals P2. Our conditions are the same as they were for a confidence interval. We need 2 independent random samples or 2 groups from a randomized experiment. 10% condition if we're looking at random samples. If we're looking at an experiment, we do not need to worry about the 10% condition. And then the large counts condition. So, next problem. Researchers designed a study to compare the proportion of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students from School 1 found that 19 missed breakfast today. At School 2, a simple random sample of 150 students included 26 who missed breakfast today. More than 1,500 students attend each school. Did the data give convincing evidence of a difference in the population proportion at the alpha equals 0.05 significance level? State appropriate hypotheses for performing a significance test and check the conditions. So, hypotheses. The null hypothesis is going to be P1 minus P2 equals 0. And in this case, P1 minus P2 that does not equal 0 will be our alternative hypothesis. P1 is the true proportion of all students at School 1 who missed breakfast today. P2 is the true proportion of all students at School 2 who missed breakfast today. Conditions. We have independent random samples. It specifically says that. 10%, it says that both schools have over 1,500 students, so 80 and 150 are less than 10% of the number of students at both schools. And then check the large counts. How many students missed breakfast, how many students did not miss breakfast at each school. All of those are greater than or equal to 10. So our conditions are met. Now, to calculate this test statistic, you're going to use the same basic formula, statistic minus parameter, divided by the standard deviation of the statistic. So Z, which is our test statistic, is going to be the statistic, which is p hat 1 minus p hat 2, minus 0, which is what we claim in our null hypothesis, over the standard deviation of the statistic, which is that formula there. Now, p hat 1 and p hat 2 are not the same as p1 and p2 in the denominator, so be very careful with that. So, a significance test begins by assuming P1 minus P2 equals 0, or P1 equals P2. Unfortunately, we don't know the common value of P, or in this case, what both P1 and P2 are. So to estimate this, we can combine or pool the data from the 2 samples and pretend that they come from one larger sample. p hat without the subscript is the combined percentage of success, or proportion of success. You do the number of successes in both both samples divided by the total number of individuals in both samples. And this formula is again on your formula sheet. Right here, when it says when P1 equals P2 is assumed, we have this formula, which is another way of writing the same formula that's on the slide. And they say P hat sub C, C for combined, is this formula here. X1 and X2 are the number of successes in each sample, N1 and N2 are the size of each sample. So, for our two-sample Z test for the difference between two proportions, if the conditions are met, and we're testing the hypothesis P1 minus P2 equals 0, you first need to find the pooled proportion of successes in both samples combined. Then we can compute the standardized test statistic. Then we want to find the p-value by calculating the probability of getting a z statistic that large or larger from this in the direction specified by the alternative hypothesis in a standard normal distribution. Same process as we did in Chapter 9, it's just we have a more complicated formula here for our test statistic. So let's go back to the school example and looking at how many students ate breakfast. We have a table here that summarizes the data from the independent random samples of children at School 1 and School 2. We have already confirmed that the conditions are met. So first, we want to explain why the sample results give some evidence for the alternative hypothesis. Remember that the alternative hypothesis is that the proportion of students who eat breakfast or do not eat breakfast at each school are not the same. So, if you look at the proportions here, 19 out of 80 students did not eat breakfast at the first school, 26 out of 150 students at the second school did not eat breakfast. Those proportions are not the same, or p hat 1 minus p hat 2 is not 0. So that gives some evidence in favor of the alternative hypothesis. Now we need to finish the hypothesis testing to see if it's statistically significant. So, you can calculate the standardized test statistic. First, you have to find the pooled proportion of students who did not eat breakfast. Then you plug everything into the Z formula. You get that your test statistic is 1.17. Then we need to calculate the p-value. Using technology, that's normal CDF. Your lower would be 1.17, which is what you got from the test statistic. Upper is 1,000. Your mean is 0, standard deviation is 1. And since it's a two-tailed t-test, it's not equal to, you have to multiply that value by 2. So we get a p-value of 0.242. Now we need to make a conclusion. So, because the p-value, 0.242, is greater than our alpha value of 0.05, we fail to reject the null hypothesis. There's not convincing evidence of a difference in the true proportion of students at School 1 and School 2 who skipped breakfast today. Again, we can do all of this in the calculator. If you are using the TI, you are looking at a 2-prop Z test. So I'm going to flip over to my calculator. I go to Stat, Tests, 2 prop z test is number 6. Then we fill in our information. X1 is the number of children who skipped breakfast at school 1 over the total number of students in the sample. X2 is the number of students who skipped breakfast at school 2. And N2 is the number of students in the sample at school 2. Our alternative hypothesis is not equal to. And then I want to calculate that. We get our test statistic, which is z, and our p-value. Then it also calculates p hat 1, p hat 2, and p hat, which on the formula sheet is p hat c for us. Remember, the formula for the two-sample z statistic for a test about p1 minus p2 often leads to calculation errors by students. So, using the calculator's 2 prop z test feature is a good idea. Make sure that you name your procedure, which is 2-sample z test for p1 minus p2 in the plan step, and record all of the values from the calculator, particularly your test statistic, which is z, and your p-value that you get from the calculator in the do step. Let's look at another example here. High levels of cholesterol in the blood are associated with a higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. The volunteer subjects were assigned at random to one of 2 treatments. 2,051 men took the drug gemfibrozil to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. During the next 5 years, 56 men in the drug group and 48 men in the placebo group had heart attacks. Do the results of this study give convincing evidence at the alpha equals 0.01 significance level that gemfibrozil is effective in preventing heart attacks? Then interpret your p-value. So we're going to do the whole hypothesis test, starting with state. Our null hypothesis is going to be PG minus PC equals 0. Our alternative hypothesis is PG minus PC is less than 0 because we're looking at whether gemfibrozil reduces heart attacks, which means the proportion of men who took gemfibrozil should be less than the proportion of men who took the placebo. And there's a typo here, I apologize. This should say PG, not P1. It's the true heart attack rate for middle-aged men, like those who took gemfibrozil. And it should say PC, not P2, is the true heart attack rate for middle-aged men, like those who took the placebo. And we are looking at alpha equals 0.01. State, we are doing a 2-sample z test for PG minus PC. We have a random assignment. It tells us that subjects were randomly assigned to the 2 groups. Since it's an experiment, we don't have to worry about the 10% condition. And then check the large counts. There are more than 10 men who had heart attacks and did not have heart attacks in both treatment groups. Do. Calculate P hat G, and I'm sorry, the second one should say P hat C, and calculate the pooled proportion. Do the math, get the test statistic, then calculate the p-value. We can also do this in our calculator. If I clear out what I had earlier, if I go to 2 prop z test, oops, I have 56 men in the drug group who had heart attacks out of 2051, and 84 men in the placebo group who had heart attacks out of 2030. My alternative hypothesis was less than. And I can go ahead and calculate. So I get my test statistic as negative 2.47, which is the same that we got using the formula. And then my p-value is 0.00675, which is the same as what we had here. Conclude. Because our p-value of 0.0068 is less than our alpha value of 0.01, we reject the null hypothesis. There is convincing evidence of a lower heart attack rate for middle-aged men like those who take gemfibrozil than for those who only took the placebo. Now, part B says interpret the p-value. Remember, when you were interpreting the p-value, assuming that the null hypothesis is true, and in this case our null hypothesis was p1 minus p2 equals 0, or pg minus pc equals 0. There is a 0.0068 probability of getting a difference, gemfibrozil minus placebo, in heart attack rate for the two groups of negative 0.0141 or less, just by chance, involved in random assignment. When you are interpreting the p-value, it is always, assuming the null hypothesis is true, there is a, whatever your p-value is, probability of getting a result this extreme or more just by random assignment, or if it was a survey, by random selection. And that's it for section 10.1.